Hello everyone, this is lecture 40 of PEC. We have introduced the nonlinear resistors in the last lecture. We will introduce two kinds of the analysis methods for the circuits containing nonlinear resistors, that is, the analytical method and the graphical method. First, we take an example to learn how to solve the circuits with nonlinear resistors by using the analytical method. As shown in the figure, the circuit contains a diode. Its UI features are known. Obviously, it is a nonlinear relationship between U and I. Because we want to solve the voltage U, so we'd better express this current by the voltage U. We can see this is the voltage U for the circuit on the left. It is a linear resistor circuit, so we can write its UI expression. That is for the resistor by using the KVL. This I equals US minus U over R. At the same time, it also equals US times e to the power of U over UTH minus 1. So we get a transcendental equation with the variable U. We can get U by solving this equation. Because it is a transcendental equation, it is difficult to solve. Next, let's look at the node voltage method. We want to solve the only independent node voltage in the circuit. This includes two nonlinear resistors. Their UI features have been written out here. We can find that they are all voltage-controlled type nonlinear resistors. Recall that the node voltage method is to write the KCL equations with the variables of the node voltages. So we need to write a KCL equation on this node. We can get I1 plus I2 plus I3 equals 0. For the current I1, according to the KVL, I1 equals U minus 2 because the resistance is 1. So I1 equals U minus 2. For the resistor 2, similarly, according to the KVL, considering the nonlinear relationship between U and I, we know that it is equal to U minus 1 to the power of 5. For I3, similarly, according to the KVL, we get it is U minus 4 to the power of 3 equals 0. This is a quintic equation about the node voltage U. We can find the value of U. Of course, the solving process is also difficult. Before continuing, I need to point out that it is reasonable to solve this problem by the node method. On the one hand, of course, it has only one independent node. This is one reason. Another very important reason is that all the nonlinear resistors are the voltage-controlled type. You must as well change this resistor to a current-controlled type. For example, U3 equals I3 to the power of 3. You try again using the node method to solve, you will find it is difficult. That is to say, for the circuits containing the nonlinear resistors, if we want to solve it by using the node voltage method, it is best that all of the nonlinear resistors are the voltage-controlled types. Then we use the loop current method to solve one branch voltage, U3. Recall that the loop current method is to write the KVL equations with the virtual loop currents. The directions of the loops have been given in the figure. Okay, we write them one by one. First, for loop 1, we write the KVL on each branch. It is R1 times IL1 plus R2 times IL1 minus IL2. The reason is that on the branch, the directions of IL1 and IL2 are opposite, so that is minus US equals 0. This is the first loop. When we turn to the second loop, this element is a nonlinear resistor. It is a current-controlled type, and this branch current I3 is equal to the loop current IL2. So we know that 20 times IL2 to the power of 1 to the third to the 3, that's U3 minus U2. That is minus U2 times IL1 minus IL2 equals 0. We can simultaneously solve the nonlinear equations containing IL1 and IL2 and get IL1 and IL2. After getting IL2, U3 can be calculated. Of course, the process is also difficult. Well, let's analyze the characteristics of the analytical method for solving the nonlinear resistor circuits. First of all, for solving steps, we need to use the KCL, KVL, and the component constraints. Here, the component constraints become the nonlinear relationship between the voltage and the current. After listing the nonlinear algebraic equations, if the solving method is accurate enough, you can get the exact solution in principle, but as equations shown previously, solving the nonlinear algebraic equations itself is a difficult problem. We need to adopt a number of numerical methods to solve them, so it is difficult to obtain the exact solution actually. You can also find the drawbacks of the analytical method through the analysis just now. First, writing equations is difficult relatively. Secondly, solving equations is also difficult. So you can find that the node method and the loop method we have taught previously can be used in the nonlinear resistor circuits, of course, but they are subject to the certain restrictions.